Okay, good, thank you. So, in 1992, Andrew Appel wrote this amazing book, Compiling with Continuations, which immediately gave me an inferiority complex because GHC, my compiler for Haskell, did not use CPS. He was essentially saying all decent functional language compilers should use continuation parsing style and was not doing it. So I was very relieved when Cormac Flanagan, Cormac, are you here? Yes? Cormac wrote this paper with some colleagues that said, don't worry about Andrew, it's all fine. You can get all the benefits of CPS using administrative normal form, which more or less what GOC was doing. So we then I had a maggot of doubt, a little worm, but I thought I was basically happy. And then 15 years later, my own colleague Andrew Kennedy wrote this paper, again with some colleagues of his, who said, no, CPS actually really is important, and there's stuff you can't do in direct style. And this paper, so the maggot turned out to be an anaconda, really live one who was eating my performance. And so this talk is about how to solve that problem and gain all the joy of CPS with none of that turning yourself inside out pain. Here is another way to look at what's happening in this talk. You will know that from natural deduction, which is a presentation of logic, the lambda calculus arrives in a kind of inevitable canonical kind of way. And GHC has used lambda calculus as an intermediate language for a very long time. Zena Ariola, though, at the University of Oregon, had said to me for some time, look, Simon, there's another presentation of logic, sequent logic, which in the same canonical way gives rise to sequent calculus. Wouldn't that be a great intermediate language for your compiler? So we did quite a bit of work on that, led a lot by Luke, who's waving from here. So this is Luke, I think, a little younger. And so we had a paper last year about that. But I wasn't satisfied with this because it still seemed a bit too complicated. So this talk is about how to make it really, really simple. So I'm going to save you the journey through this valley of complication and just give you the simple answer, which will then make you, hope happy. So first thing, a little bit of background, commuting conversions. This is what good compilers do. So imagine that you have stuff on the left is code from the prelude, some definitions for null and not for lists and booleans, and here is the definition of not null, which is just not of null of x's. Now, if I take here, like compilers do, and I inline not, that gives me a case expression which wraps around the null, turns true into false, false into true. Then if I inline null as well, I get a case that scrutinizes the case. Now, the outer black case, think of it as a crocodile that is eating the inner case. So the outer black crocodile wants to eat this case, and one way he can do it is by cloning himself and moving into both branches like this. So here he is, the outer crocodile has duplicated himself, but is now scrutinizing true here and false here. And now we can say case false, oh, that's easy to simplify, this is easy to simplify, and we get this code, which is of course the code that you would have written by hand for not null anyway, okay? This is called commuting conversions. All good compilers do it. It's been around for years and years, ever since Guy Steele wrote his Rabbit compiler before I was born. So this is hardly new stuff. So, but there is a problem, which is you can duplicate code like this. Suppose the outer crocodile was really big and fat. Right, so here he is, he's got big 1 and big 2 are his big legs, right? So if you duplicate him, his legs are going to get duplicated. That's not good for compilers, you get lots of code. So how can we avoid gratuitous code duplication? Well, you just let bind it, right? Supposing you bind J1 and J2 as auxiliary local let bound functions. Don't ask me why there's a unit parameter for here. This is just keep the ML crowd satisfied, right? So, and now we can duplicate the crocodile by having let bound his legs. Does that make sense? So now, and the good thing is that having done that, and we now simplify this term, we get this one, right? And now J1 is only called once, and existing inlining heuristics say if a function is only called once, then inline is its call site, and you get back the same code that we would really have liked, because big 1 and big 2 don't actually, as it turns out, need to be duplicated. So far, so good? Okay. Now, this join point idea, right, so I'm going to call these J's join point, this idea scales well when the patterns bind variables. So here's an example where this outer case, the crocodile now has a baby, so it binds a variable in this pattern, so big has x mentioned free. But that's just fine, because instead of having a unit function, you can have a function that's abstracted over x, and so you just pass x from the call sites. Okay, so this is just a remark to say, all this scale's fine. We have existentials, GADTs, all of that, everything is fine for this plan. Okay, so that's end of background. What then is the problem? So here is the, I've got to say one more thing. These join points, these let bound functions, I call them join points because, of course, they really are control flow labels. They are not heap-allocated closures, right? That would be bad for performance. Because what's really happening is, in this example, I'm taking x's. If it's one, I've got two cases, then I'm testing E1 and E2, and then I go to J1 and J2. So the operational semantics of these join function-y things should simply be adjust the stack pointer and jump, right? That's what it should be. And GHC has done this for years, as have many other compilers, as a back-end optimization. Just in the code generator, it knows how to do this. So what properties does a let binding have to have in order to make it have this nice, fast implementation? Just that all the calls to it are tail calls, that they are saturated tail calls, and by virtue of being a tail call, they're never captured in a thunk or a closure. That's a sort of rough intuition behind what these join points are, okay? So these special bindings will compile particularly efficiently. Very good. Now, the maggot that turned into an anaconda is this. Join points are nice and efficient, but you don't want to lose them during other program transformations. So here is an example in which I've got the outer crocodile scrutinizing this inner stuff, which already has one of these let j guys. Now remember, this let j is not meant to allocate, it's a join point. It's going to be really efficiently implemented. But if I just move the outer black crocodile around the inner pieces, look what has happened. Number one, J is no longer a join point. It is not tail called here, right? It returns to this case. Oh, no. And secondly, this case here is scrutinizing this J guy, and really he wanted to get his crocodilian teeth into E1. That's where the juice is. That's where the nourishment is in here. This JX doesn't tell us anything, right? So here in E2, he can look into E2, but he's stuck on this guy, okay? So two big problems, a transformation that looked as if it was going to improve matters and making things worse. So what we really want to do, of course, is to instead move the crocodile into the right-hand side of the join point. So I've changed this from, instead of calling it let, I'm now saying join. I'm dignifying it by naming it as a distinguished kind of thing, a join point. And when I move the crocodile into the right-hand side, I'm going to move it into the right-hand side of the join point here. Right, so this is the, if you're going to remember one slide, this is the slide to remember, right? I want to move for the distinguished things that are let-bound join points, I want to move the outer evaluation context into the right-hand side of the join point. That's thing number one, as well as the body, right? The crocodile still eats E2. Don't forget that, right? But if the crocodile meets a call to J, right, that's this call, he evaporates, because he's already gone into J's right-hand side. Does that make sense at an intuitive level? This is the intuition. Really simple, right? Identify the join points, move the crocodiles into the right-hand side, they evaporate when they hit a J. That's it. You understand that? You've understood this paper. How are we doing for time? Where's my session chair? Yes, good. How many? Okay. Good, right. Okay, excellent. So, solution to this little conundrum then. So here's the problem. So GHC was really doing this, right? And it was occasionally behaving badly for us. So the solution then is to just identify join points as a language construct. And as I was saying, we came to this in a very long way. The story about the sequent calculus indicates that this particular game isn't just a little ad hoc game. It has rather deep roots in logic, right? So that was reassuring. That encourages you to believe this might be the right thing to do, not just another random hack. But here is what we ended up doing as a way to retrofit this onto a direct style language. So here is GHC's intermediate language, more or less. It'll be very familiar, variables, constants, lambdas, applications, big lambdas, constructor applications, case, let, and. So we're going to introduce join here. So this is one of those join point bindings. JB is one of these guys. He's a binding of a join point, and I'll come to recursion in a second. And then the jumps are these guys here, which I've still written here as just a function application, but I'm going to distinguish them too, so that I know at the point at which I'm making the jump, this is just a jump. Operationally, it's just a jump. Make sense? So that's the language. So we're going to formalize join points in the language, and then, so that's this first part. We're going to identify them as a distinct language construct. Then we're going to exploit join points when we're making these commuting conversions. And the third piece is that we're not going to ask the programmer to decide which things are join points and which are not. No, we are going to infer which let bindings can actually be turned into join points, just as we did right here. I moved very quietly from let here to join here. That is a little analysis, and it turns out to be really, really simple. It's called quantification. You can find whole papers about it, but it's, it's really, really very simple thing to do. Okay? So let me just say this exploit business. What is the exploitation? Well, in the paper you'll find a table of transformations, so which we typically use left to right, equalities between terms of the language, and the ones that are most important for the purposes of join points are these. Look, so E is the crocodile, right? He's the evaluation context that is eating a term. So you should think of it as a case expression or composition of case expression, some kind of strict evaluation context. When he eats a let, well, he just eats the body of the let, and the bindings float outside. When he eats a join, oh, look, the crocodile moves into the right-hand side of the join point and into the body. Remember, it moved into both places. And then the other half of that is that when the crocodile meets a jump, he evaporates. He simply doesn't appear altogether. There's a little bit of wiggling with types to make sure that the types all work out. Does that make sense? Because, of course, when I push the crocodile into the right-hand side of a join, the result of the join point has changed its type. Okay? So really simple. Very, very easy to add to a compiler. One more thing that, again, everybody who does this realizes after a bit is that join points can be recursive. Right? So as well as I've just shown you non-recursive ones so far, but here is an example of a recursive one. Here's a tail recursive function last, which extracts the last element of a list. I'm going to ignore the empty list case for now. If I introduce the recursive join points, here it is. It's just think of it as like a let rec. Remember, the semantics of join points are precisely the semantics of let. Right? You could just forget joins and write let everywhere, and you get the right meaning, not the right operational semantics. So just imagine this is a let rec, right? So here it is. This is really the definition of last, but expressed with join, and then here's an invocation of it. And what does this little transformation do? It's pretty much embodying the idea that tail recursive functions could be implemented as loops, right? Because this here is just a jump to the beginning. Now, GHC's backend, like everybody else's backend, has some ad hoc wimwams to make tail recursive functions turn into loops. This allows us to expose it in the actual term language itself and then expose that to further optimization. Okay, so I've said a number of things about operational behavior, so it's reassuring to know if you claim that something has an efficient operational implementation, it's good to know that it really does have. So the paper also has a little operational semantics that I hope will, I'm not going to go through it, but I hope it'll make you believe that yes, if that semantics works, that operational semantics, that is, it's sound with respect to the semantics of the language, then indeed the implementation in terms of labels and jumps should be fine. All right? That's all that happens in there. So we implemented this in GHC. Well, more precisely, Luke implemented it in GHC. Right? We just locked him in a dark room for about 2 days, and there it was. So GHC is a big 25-year-old optimizing compiler. There's lots of code in it. So it's not a trivial thing to change the IR of a compiler like that. But it turned out to be very nice and easy to add, partly because join points really do share a lot in common with letrec, which was there already. So more or less, it's just a variant of letrec, and actually it participates in a lot of letrec's existing transformations, namely strictness analysis and inline decisions. They work uniformly for join points and lets, which is really good, right? You say you don't have to repeat all of that. But there are some places, each call pass, each transformation, needed adjustment to say, sometimes you turn a join point into a non-join point. So in fact, we learned new places where GHC, new maggots, were discovered, right, by this process, and then we fixed up the pass, so it no longer destroys any join points. So finally, the process of inferring join points, quantification, turned out to be really easy. Okay. Now, I know at this point in the PLDI presentation, everybody's hoping to get a graph that shows, 20% speed ups. I would love to be able to show you that. Actually, a lot of the low-hanging fruit has been shot down already, right? So this is, 0.4%. Is all we get on allocations, So yay for optimization. Sorry about this. So the thing is that good compilers have to have a lot of bullets in their gun, right? And our existing bullets had already been pretty extensively exercised on this benchmark suite. I'm hoping that maybe some new, sacrificial animals that walk into the space may be shot down more easily. But But what I really like as a compiler implementer is that optimization is much more robust, right? So previously I was fragile to, remember those let j's? If we were to inline them in the old scheme, good things would happen. And if I don't inline them, then bad things happen. So it was fragile to the degree of inlining that happened. And now it's completely independent of how good inlining is. So that is really, it just makes things much more robust. It also nails some inner loops to zero. So people, performance critical people, write code in a particular style that sort of guarantees good behavior. And some of those loops actually in our benchmark suite just went from, allocating lots to allocating absolutely nothing at all. That's really very satisfactory. But most intriguingly, the thought I'm going to leave you with is that it actually can affect programming style. So here is an unexpected bonus that we literally had no idea would happen to us. Those of you who've been, who are obsessive readers of the ICFP proceedings will remember a paper by Roman Ochinsky and his colleagues, Duncan Coutts and so forth, about streams. Now, a stream is a kind of representation of a sequence, and it has a stepper function, so a state and a stepper function. The stepper function says either, given a state, it will either say it's the end of the stream, or it will yield a new member of the stream and a new state. And with this representation of streams, you can write functions like filter that takes a filtering function and takes a stream of A to a stream of A. And here's the code, which I'm not going to go through, but I will call upon you to note that the stepper function is recursive, right? And that screwed fusion. So things like filter of filter did not fuse. So Roman and his friends said, let's add a new constructor to this type, skip, that says, I'm neither at the end of the list, nor can I give you an element, just skip. And that kind of worked, but it had other bad consequences. And the thing we discovered is that with join points, you don't have to do that. Step is a join point. Look at it, it obeys all the rules. It's only tail called, right? Always saturatedly. Skip is a join point, a recursive one. And so this happens. So I'm just schematically showing what happens. Here is that join rec of step. And what happens when you try to do fusion is you have a case that scrutinizes it. So there's the crocodile. Crocodile's turned red in this for some reason. And he moves around the right-hand side, remember? So he moves around the case done, the case yield. He evaporates at the case step, and he evaporates at the jump in the body. So these are the points where the recursive function returns. So in effect, the consumer of this recursive function has moved to the very places that it returns. That's very, very cool, right? So now we can have skipless streams. I'm almost done. But 1 minute?
Yeah, 3 minutes.
3? Oh, 3. Right. Well, so we're going to have more time for questions. This is good. Right. So the thing I want you to remember from all this is that it's kind of almost embarrassingly simple idea. Right? Why did we not have this? Why did I not have this idea 20 years ago? Why has GHG not been using it all this time? It's so simple. It has a really good power to weight ratio. How much work you have to do in implementation terms compared to how much benefit you get, and it just makes your compiler more robust with fewer special cases. So really, if you're building a direct compiler, I think everybody should use join points. And I will finish with a sort of piece of provocation, which I'm hoping that those CPS addicts in you, Mark Feely, are you here? Yes, Mark at the back, right. So this is for you, Mark, right? So is it time to give up the drug of CPS in favor of the simplicity of direct style? So there's a section in the paper about this that tries to be a bit more scholarly about it, but here's a sort of rough summary, right? That CPS is indeed very cool, right? And I was passionately excited about it when I discovered it, but it does fix order of evaluation, which is not so good for a lazy language where we quite monkey about with order evaluation quite a lot. And it does make some transformations at least significantly harder. Common sub-expression elimination and applying rewrite rules, user-written rewrite rules, becomes significantly more difficult. So adding join points sort of gives you really all the advantages of CPS, but this is the question: is it all the advantages? So my challenge to the Marks of this world are: show me the next round of this bout, the places where CPS is going to do something that none of this can do. And maybe such things exist, but I'm waiting in excitement and hope. Thank you. Yeah, not Mark, somebody else. Yes, call CC, right.
Can you please repeat the question?
Oh, sorry. The CPS gives you constant time call CC, right? Which is, so in language with the call CC, that's super important. Though I always wonder about the constant time call CC. That just, when people say something is free, they usually mean that it's already paid for. And that is the case with quotes, constant time call CC. So, but with that caveat, so of course, I mean, CPS is incredibly insightful in all dimensions. Mark. So I can't hear you, Mark. Ah, Gambit. For the record, Gambit does not use CPS conversion. I'm shocked. Anyway, go on. Yes, yes. So Mark's point is that maybe this is CPS conversion plus beta reduction munged into one step. And another way to put this is, Olin told this to me. He said a CPS-based compiler is focused on lambdas, and your compiler is focused on lets, right, which are a bit like the, we've done a bit of beta reduction at the same time. So maybe there's something in that. And indeed, the sequent calculus, of course, from which a lot of this arose, is very focused on, there's a duality between terms that produce things and continuations that accept them. So yeah. Anyway, there was somebody else. Yeah.
And so does your compiler come with a garbage collector?
Oh.
And if so, how do you explain the interface between the compiler and the garbage collector for traversing the stack? And is that because you have a stack?
Yes, we do. So we do have a garbage collector. You'll be astonished to learn. And yes, threads do have stacks. And yes, the garbage collector does traverse them. So does that answer the question?
Oh, isn't that, like, complicated?
Yes, but it's fast. And quite a lot of, even in the CPS world, I think people, is it not true that like Manticore, for example, uses stacks precisely to get performance, even though it is a CPS-ish compiler. So there's and again, I think you could use this direct style, and right at the back end, you could atomize it into heap-allocated stack frames in the manner that you have so persuasively and articulately advocated for so long. So I think that could be, you could regard that almost as a kind of code generation technique, if you like. And so please go ahead. Yeah, come on.
Simon, nice work. I have one question. When you move an evaluation context inside a joint from binding, you end up duplicating it, both the joint thing and in the body of the joint.
Yes. Yeah.
Is that a problem? So the second
No, it's so yes. Look. Now I have to stay here. This is very difficult. So in the second line, right, E is duplicated. True. But of course we can save that duplication in precisely the way that we did back here, right? We can just let bind them. So if the thing that you're duplicating, the evaluation context is big, well, just let bind some more join points, right? So the bit you're actually duplicating is, that's right. So it's turtles all the way down, yeah. So we get a lot of join points, and then we end up inlining a lot of them or collapsing a lot of them. So we introduce them freely, and then they go away through inlining.
Yeah, time for questions if you want. Next speaker, pretty sure.
Great, okay. Thanks.